So in this section we're going to look at two things in particular. The half-life of a substance and artificial radioactivity. We've already looked at natural radioactivity in section 6.3, and today we're going to look at how humanity is able to create a radioactive element from one that is not. First of all, for the half-life is the rate of time that it takes for the radioactive element to decay. Now, not all of that element will always decay. What happens is half of it will decay over a certain length of time into another element. And then that half that is left over as radioactive will decay again in the same amount of time to half of that, and so on and so on and so on. The rate at which it decays is called the decay constant. There's a mathematical way of modeling exactly how fast the element decays, but that's not important to us. Some elements decay extremely quickly, much less than 1 second. Other elements decay over a matter of billions of years. Well, let's take, for example, thorium-234. Has a half-life of 24 days. So if we start with 500 grams of it, 24 days from now we'll have 250 grams that have decayed and 250 grams still present as thorium-234. After another 24 days, giving us 48 days in total, now we'll be down to 125 grams of thorium. After 72 days, we'll be down to 62.5 grams, and so on and so on and so on. So with these radioactive elements, even though they do decay into other elements, not all of the radioactive element will always decay. There will always be a small amount left over as that original element. If we take a different element, now that has a half-life of 12 hours, just a little bit easier to graph out, we can take a look at the activity and the way the time goes. So if at 0 hours this element had an activity of 2 times 10 to the 8 becquerels, after 12 hours it would be 1 times 10 to the 8, 24 hours would be 0.5 times 10 to the 8, and so on and so on. And as we can see in the graph, as we plot those points out, that graph asymptotes out at the bottom towards an activity of 0. It will never quite reach it because we'll always be dividing the activity in half, so there will always be some radioactive element left. As I mentioned before, half-lives differ. The shortest half-lives that we know of, 10 to the minus 16 seconds. The longest that we know of, 10 to the 20th years. Some common elements have their half-lives listed in that table. So hydrogen-3, 12.3 years. Carbon-14, used extensively in dating fossils and such, 5,730, and so on and so on. Uranium-238, the most common form of uranium, 4.5 billion years. So that's half-life in a nutshell. But what about artificial radioactivity? Well, we know that many elements are naturally radioactive. They will decay on their own. But we can actually force stable elements to become radioactive. What the Curies did when their experiments, they took non-radioactive elements, they bombarded them with neutrons, and essentially increased the mass number of the element. So one element they did this with is cobalt-59, which is naturally occurring. It's non-radioactive. They added 1 neutron to it, as shown in that chemical equation, and they formed cobalt-60. Well, cobalt-60 is radioactive. In nature, there is some cobalt-60, but most of the cobalt-60 we know of is actually artificially created. Cobalt-59 is incredibly common, and it's relatively easy to make it accept a neutron into the nucleus. So cobalt-60, when it decays, we have beta particles, electrons, as well as gamma rays. The gamma rays produced by cobalt-60 are actually of just the right energy to be used in cancer treatment. So when you hear about somebody undergoing radiation treatment for cancer, that radiation source is cobalt-60. As a side note, The major producer of cobalt-60 in the world is actually in a place called Chalk River, Ontario. There's a nuclear reactor there that produces over 90% of the world's cobalt-60. Another use of radioactivity is carbon dating, which I've mentioned before. Carbon-14 is a naturally occurring isotope of carbon. It makes up approximately 8% of all the carbon that's in existence. The way it's formed is in the upper atmosphere, radiation from the sun and from cosmic rays bombards nitrogen with neutrons. That nitrogen being bombarded with neutrons creates a radioactive nitrogen, which decays into carbon-14. When that carbon-14 is allowed to combine with oxygen, it makes things such as carbon dioxide, as well as other carbon compounds that are ingested by living things. Those living things are constantly ingesting carbon-14, and eventually we get to a steady state where there is a constant amount of carbon-14 in our system. We take it in, we excrete it out, but as time goes on, we get to a steady state of carbon-14. Once we die, or once the living thing dies, there's no more carbon-14 being ingested into the system. So now the carbon-14 is only decaying out of the dead organism. By using some techniques, we're able to detect what percentage of carbon-14 is in a particular fossil or bone. And based on what percentage is left, we're able to use the half-life of 5,730 years to determine how long has passed since the sample died. That dating is actually quite accurate. It's accurate to within about 50 years, especially for items that are in that 2 to 5,000 year old range. Carbon dating is less accurate for very young or very recently dead organisms, as well for very old organisms. So something more than 25,000 years old, carbon dating would not be a very effective way. It would give us a good estimate of how old the object was, but there's other ways of dating it with radioactivity that are better than carbon-14 once we get to that kind of age.